Today we're talking about Hess's Law. Now I want to start with sort of where Hess's Law fits into the whole plan of things, and that means taking a quick look at what we know so far. What we've done so far is we've talked about thermochemical equations, which is basically just a reaction equation that has the energy somehow indicated. And we can indicate them several different ways, but what's most important right now is that we understand this method where the enthalpy term is attached as almost a separate term at the end, and we can recognize both the exothermic and the endothermic because that's going to be kind of key. The second thing is we know how to do calorimetry at this point, which means we know how to actually do a reaction and measure the energy involved in that reaction, whether it's energy released or energy absorbed. So Hess's Law is going to be sort of the next piece of that, and it's going to kind of use both of those things. So what is Hess's Law? Hess's Law, in short, is a thing that allows us to manipulate reactions and treat them algebraically in order to rearrange them to calculate the energy in reactions that we cannot actually do easily or at all. So in other words, if I have a reaction on paper that cannot be done for real in reality, but I want to know the energy that would be, then I can use Hess's Law. And one of the things that we're going to make use of is the law of conservation of energy. So if I take a reaction that I could do, and I have a number 4, if I were to double that reaction, I would also double the amount of energy. Law of conservation of energy, but also this notion of treating it algebraically. Whatever I do to one side of the reaction, I'm going to do to the energy side of the reaction. And the other thing is, if I were to take that reaction and turn it around and reverse it, now I probably could not do that. Well, for this one I probably could, but for some reactions I could not actually do the reverse reaction. But again, law of conservation of energy says that if I could, the amount of energy involved would be the exact same amount, just now in this case endothermic, where the original one had been exothermic. Okay, and those two key ideas are going to be absolutely fundamental in doing Hess's Law question. So dive right into Hess's Law question, and what you'll end up with is you'll be given a target reaction of some kind, a reaction in order to solve, but you won't have the ability to do that particular reaction. Now a little bit later we'll talk about what it means for something to be an enthalpy of formation, although we've probably already said what a formation reaction is. But suffice to say at this point, if you were to take 4 moles of carbon and 5 moles of hydrogen gas and put them together, it doesn't matter what you do, what kind of witchcraft you attempt, you would not get C4H10 out of that. So this reaction is not realistic in terms of actually being able to do a reaction. But on paper it looks great, which means I should be able to calculate an energy for it. So in this case, I happen to be given 3 different reactions to work with. And what I'm going to do is use Hess's Law, manipulate those reactions in order to calculate the energy that that reaction would have if it could have. So I'm going to keep my target reaction up here. And there's a variety of ways we can approach it. What I like to do is I like to start with the reactant. I find the reaction of those 3 that I'm working with that gives me the reactant where I need it in the right amounts. Quick look says I don't have that, obviously, but I do have carbon in that thing. So I'm going to look for carbon. I'm going to look for the reaction that gives me carbon. And reaction number 2 has carbon as a reactant, carbon solid. It doesn't have enough, so what I'm going to do is I'm going to manipulate it algebraically. I'm going to multiply by 4 so I get the 4 moles of carbon that I need. That means I multiply everything by 4, including the energy term. So that gives me carbon where I need it to be. It also, though, introduces a slight problem that I'm going to have to fix, and that is it gives me 4 carbon dioxides that are not in my target reaction. It also gives me oxygen, but I'm going to leave that to the end because every one of those reactions had oxygen in it, so I'm going to deal with the carbon dioxide. So now I skim through those reactions and I try to find the one that has carbon dioxide as a product. Turns out it doesn't. Sorry, carbon dioxide as a reactant. Turns out none of them do, but one of them has carbon dioxide as a product, which means if I were to reverse that reaction, then I've got the 4 carbon dioxides that I need, no longer as a product, but now as a reactant, which will allow me to cancel them out. So any carbon dioxide that got theoretically produced is now going to get reacted in the next reaction. I also want to pause here for say something that I should have said earlier. You'll notice that on the far left, I'm saying exactly what I'm doing to the reaction. I'm saying which reaction I'm using, number 2, number 1, and I'm saying what I'm doing it, times 4, times -1, or REV for reverse, because that communicates to the people who are looking at this, because maybe somebody's marking this and they're trying to figure out what I'm doing. So giving them a little bit of a heads up as to what I'm doing is just a really good idea. Okay, so I've gotten rid of the 4 carbon dioxides, or eliminated, I canceled out the ones that I had used in the first one, but then got, produced in the first one, but then used up in the second. But it also gave me C4H10 on the product side, which is excellent because that's exactly what I need, exactly where I need it. On the other hand, it gave me these waters that I don't need. So it solved one problem, accidentally solved another problem, introduced a third. But I go back to my reaction sequence and I find a reaction that has 5 waters in it. Well, it doesn't have 5 waters, but I can get it to give me 5 waters by multiplying by a certain amount to give me the 5 waters that I need. At that point, I can cancel the 5 waters out. And now I want to take a quick look at what else do I have. What else did that reaction do? I used it to eliminate the 5 waters that I needed to, but it also gave me 5 H2s, which is excellent because I needed those anyway. Okay, at this point, I've been ignoring those oxygens the whole way through. At this point, what I have is oxygens on the left, oxygens on the right, and if I add them all up, I have 6, what have I got? 6.5 on the left, and I have 6.5 on the right, which means I can cancel those out as well. Which means I've eliminated everything I don't need, I've kept everything I do need, so if I add all of that stuff up, I get my target reaction and I get the energy. And all I'm doing is I'm taking exactly the same things that I did to the reactions and do that to the energy terms, multiply by -1, multiply by 4, multiply by 2.5, add them all up, and I get the total energy. So you'll notice that Hess's Law is not all that difficult. It just comes down to trying to get to the target and then eliminating the things that we don't need. And in terms of eliminating those things, canceling these things out, crossing them out, whatever you want to call it, a couple of things you have to keep in mind is they have to be exactly the same. Exactly the same. They have to be exactly the same state. If you've got water as a gas on one side and water as a liquid on the other side, they will not cancel out because they have a different amount of energy. Think about it. You have to add energy to liquid water to get water as a gas. So they're not the same in terms of energy. They also have to have exactly the same formula. If you've got I don't know, a calcium on one side and a calcium chloride on the other side, they're not exactly the same. So you cannot cancel out parts of one without canceling out everything. And then one of them has to be on the reactant side and one of them has to be on the product side. Right? Think about it this way. It has to be produced but then also reacted, or the other way around. Okay? We don't need to think of these reactions as happening in sequence, but if you have them on the same side, they're going to combine, they're not going to cancel. And then lastly, trying to be systematic. I showed you one system that I use. I don't necessarily use it all the time, but come up with something that works for you so that you're not trying to, okay, what do I do with the first reaction? What do I do with the second reaction? Don't worry about doing the reactions in order. Think about your target because that's really what you're trying to get. So let's try another one. I'm not going to talk through the reaction too much. If you need to pause it here and write that down or get a good look at it. But my target reaction is this: 2 borons with 3 hydrogens to make diboron, that's diborane I think, but doesn't really matter, B2H6. The plan then, or what I'm going to do, same thing I did last time, I'm going to try and start with my first reactant. So got my first reactant where I need it with the number that I needed to have. In order to get that, I had to take that reaction and cut it in half, multiply by 1/2. Had to do that with everything. That gave you a certain amount of energy. It also gave me a product that I don't need, so I need to look through and find a way to reduce that, or to eliminate that, I should say, which was the first reaction, but then it needed to be reversed. So reverse the first reaction, which means change the sign on the energy, and that is going to solve one problem, but kind of introduce another one. But before I introduce the other problem, it also gave me the product where I need it to be, which is a good thing. Then it introduced this new problem of the water. What do I do with it? I look at the other reaction to try and eliminate it. Water is on the reactant side, so now water is going to be on the product side. Same amount, same state, one on opposite sides, which means I can cancel them out. And then it also gives me the 3 hydrogens where I need them to be, and it allows me to now look at all those oxygens, add them all up, and then eliminate the ones that I eliminate them, and fortunately all of them will eliminate. And I shouldn't say fortunately as if that just was lucky on my part. That will happen. If you do this stuff right, it will happen. Then add them all up. I get my net reaction, or get my target reaction, and my net energy. Okay, and that's really all there is to a Hess's Law type question. And that's, other than going back and thinking about those tips and making sure that you keep those things in mind. And also, if you are given 5 reactions, you will need all 5 reactions. If you're given 4 reactions, you'll need all 4. You should only need to use them once. Sometimes I see where people have used reaction number 1 here, and then they'll use it again there, and that shouldn't need to do that. Usually that means you're not being very systematic, or whatever system you're using isn't that efficient. Anyway, talk to you another time.